Okay, now this is the second video recording the questions from chapters 11 and 12. Number 15, conduct the following test at alpha equal 1% by determining null alternative, test the statistic p-value, assume the samples were obtained independently using simple random sampling. So we need to test that p1 is not equal to p2. When you have two proportion, this is a two proportion z-test, and he's given us the values. So for the null will be p1 the equal sign always, and h1 will be p1 not equal to p2. And then to show you how we perform the rest of the test, so you click on stat tests, you choose two prop z-test because you have two samples, enter, and now we're gonna key in the values. So x1 is 28 and 1 is 254, x2 is 38 and n2 is 301, and we need to test that p1 is not equal to p2, so you just hit calculate, and z is negative 0.58, and look at the p-value, it's a huge 0.56, so you're going to fail to reject the null hypothesis. You fail to reject the null hypothesis, and there is no sufficient evidence to conclude that p1 equals p2. You choose this. Next question. The pass completion percentage of 10 college football quarterbacks of their freshman and sophomore seasons are shown in the table below at alpha equal 5%. Is there enough evidence to support the claim that the pass completion percentages have changed? Okay, here you can see this table. You have the player 1, his completion percentage when he was freshman and completion percentage when he was sophomore. These samples are called dependent samples or paired. You don't do a two sample t-test here because the samples are paired, they're dependent. What you do, you test the difference against 0. So he's asking us if the pass completion percentages have changed. So you want to check if they are different. That means the difference is different from 0. So when it comes to paired samples, you do it against 0. I'm going to show you how to use StatCrunch to do this. The pass completion rate percentage have changed. This is the claim. And you see, you do mean of the difference. So you subtract freshman minus sophomore, and you test it against 0. And because he says have changed means different sign, you just use the different from 0 sign. So it will be this one right here. Null hypothesis will always be the equal sign. Now, how do you find the test statistic? Let me show you how to use the calculator. Okay, you go to stat, t-stat, and look, paired means dependent. Column 1, freshman, column 2, sophomore, and I want to save the difference, so the StatCrunch is going to subtract the differences, and we now want to test that mu of d different from 0, compute. And look guys, test the statistic is negative 1.52, and look at the p-value 0.16, which is more than alpha. You fail to reject the null hypothesis, and look at the differences. 67.8 minus 67.5, 0.3, it did the differences for you. You could also do this on the calculator, but you have to do the differences first, and then you take this one and put it in the calculator as L1, for example. And let me show you what you do in the calculator. So you go to stat, edit, you put the differences in L1, and then you go to stat, tests, t-test, and then data, and then you put 0 here because you're testing, and then L1, and then you do different from 0 here, and then you test it, you get the same results, exactly the same results. So you put the test statistic that we got in StatCrunch, the p-value is 0.16, which is more than alpha, so the null hypothesis would not be rejected. And then you say, since we didn't reject the null hypothesis, there is not enough evidence to support the claim that pass completion rate have changed. Okay, 17. To test the belief that sons are taller than their fathers, the student randomly selects 13 fathers who have adult male children. She records the height of both the father and son. These are dependent. You're talking about the father and son. In inches, obtain the following data. Are the sons taller than their fathers? Okay. So they are dependent. We're going to do that in StatCrunch. Okay. Sons are taller than their fathers. That means fathers are shorter than their son. So what we want the difference to be, positive or negative. Here's how I would think about it. So the claim is, are the sons taller than their fathers? But we started with the fathers first. So let's say if the father is 67 inches and the son is taller, so let's say 69. What's 67 minus 69? It's -2. Is -2 positive or negative? Then you say negative, then you test less than 0. This is how you determine which sign you should be using. So you just open in StatCrunch, stat, tstat, paired, select column 1, father, select column 1, son. So the fathers are shorter than the son. That means the difference is less than 0. Save the differences, less than 0. Hit compute, and the test statistic is 0.02. You see right here. And look at the p-value. Let me show you the p-value one more time. P-value is huge, 0.51. So the test statistic is 0.03, and look at the p-value, it's huge. So more than alpha, you fail to reject the null hypothesis. And there is not enough evidence to conclude that the sons are taller than their father. Question 19. Test whether mu1 is less than mu2. When he put mu1 and mu2, that means the samples are independent. Then he will use two-sample t-test here. Alpha is 0.02, and he gives us some data right here. Okay. So we have the sample size for the two samples. We have the mean of the two samples and with standard deviation. So this is going to be two-sample t-test. All right, so let's do that. So in order to do it, I'm going to do it with the calculator first. So clear, you go to stat, tests. And what does he want us to test? That mu1 is less than mu2. So your null hypothesis will be mu1 equals mu2. Alternative will be mu1 less than mu2. Two-sample t-test, guys. Okay, not data. I have summary, so I go back to stats. Okay, x1 bar. Let's record the data now. 103.4. S1 12.3. N1 is 32. X2 bar is 114.5. S2 is 13.3. N2 is 25. And we're testing that mu1 is less than mu2. So the second one. Now for pooled, by default, the pooled is no, unless if he says the population variances are equal, then it is a yes. So we're just gonna use no here and calculate. And look, guys, this is the test statistic, and this is the p-value. So test statistic is -3.23 and p-value 0.0011. All right. See, p-value is less than alpha. You reject the null hypothesis and support the claim. There is sufficient evidence to support the claim. A manufacturer of color candy states that 13% of the candies should be brown, 14% yellow, 13% red, 24% blue, 20% orange, 16% green. A student randomly selected a bag of colored candy. He counted the number of candies of each color and obtained the results shown in the table. Test whether the bag of colored candies follow the distribution stated above. This is, guys, section 12.1. It's a goodness of fit test. So this is how you do this when you have more than two percentages. first of all, you state the null hypothesis, which is the distribution of color is the same as claimed, and your alternative hypothesis will be the distribution of color has changed, or is not the same, or is different than expected. So that would be HO and H1. Now, in order to find the test statistic here, you need the observed values. This is what we got from when we counted the colors in the bag. And the expected values, they are based on the expected percentages. So how do we find the expected count? This is something, guys, that you have to do by hand, even if you use technology, not just to find the test statistic and p-value. So how many candies do we have all together? We need the total here. So you just add them up. 61, 63, that's 124, 126, and 50, 176, 177, 237, 307, 315, 375, 381. So you have 381. So for brown, 13% of 381 will give you 49.53. For yellow, you do 14% of 381. I forgot the total. Then you get 53.34. So you have to count the total first, guys. Okay. That you don't need. You already have the percentages. Okay. And like for green, what's a green? 16%. So you do 0.16 times 381. That should give you 60.96. Now you have the observed values, which is the frequency, and you have the expected values. We're ready to find the test statistic. So to find the test statistic, guys, I don't think we can use StatCrunch here. It doesn't allow me to use StatCrunch. So I'm going to go and put it in the calculator and show you how to use the calculator in here. Okay, so you're going to input the observed values in L1 and the expected values in L2. So I put the observed in L1, the expected in L2. You go to stat. The name of the test for this section 12.1, guys, is goodness of fit test. Observed in L1, expected in L2. Now, degrees of freedom, let me tell you what this one is. Its number of categories minus 1. How many categories we have here? 1, 2, 3, 4, 5, 6. Minus 1 will be 5. And then you hit calculate. And there you go, guys. Chi-square is 15. That's the test statistic, 15.121. And look at the p-value. It's so small, 0.0099, which is less than alpha. And p-value is less than alpha. You reject the null hypothesis. And you conclude that the distribution has changed. It's not the same as it used to be. Okay, next question. The table below lists the frequency of wins for different post position in a horse race. A post position of 1 is closest to the inside rail, so that horse has the shortest distance to run. Because the number of horses varies from year to only the first 10 post positions are included. Use a 0.05 significance level to test the claim that the likelihood of winning is the same for the different post position based on the results. Should bettors consider the post position of a horse race? Okay. He's asking us to test the claim that of likelihood of winning is the same for all. Okay, here's how we do that. Same means the same percentage. How many percentages here? We have one. How many categories we have? 1, 2, 3, 4, up to 10. So 100% divided by 10, guys, will be 10% each. So what you need to do, we have the observed values. In order to find the expected values, add them up right here. 18 plus 14, 32, 42, 44, 54, 59, 69, 74, 80, 88, and 11, 99, 105, and 11, 116. And if you divide 116 by 10, you get 11.6 each divided by 10. So these are the expected values. Let me see if I can use StatCrunch here. Yeah, we can. Okay. So these are the observed. The expected, guys, as I told you have to do some work with them. We added those, they were 116. And since he's asking me they are all the same, so you just divide by 10, which is the number of categories. So 116 divided by 10 is 11.6, 11.6, 11.6, 11.6. That's it. Now I go to stat. Goodness of fit test, chi-square test. Observed in wins. Expected we did put in a new variable called var3. And that's it, compute. And look, chi-square is 12.62 and p-value is 0.18, which is bigger than alpha. You failed to reject the null hypothesis. Look. And there is not sufficient evidence to warrant reject the claim, because the claim is in the null hypothesis, because he says test the claim that they are the same. You know, HO means the distribution did not change. H1 means the distribution has changed. So the claim is in HO, and with the claim in HO, you don't use the word support, you use the word reject. So you say, since we don't reject HO and the claim happened to be in HO, you say there is not enough evidence to reject the claim. All right, next one, this is section 12.2. The accompanying table shows the results of challenge and reference calls in a major tennis tournament. Use a 5% significance level to test the claim that gender of the tennis player is independent of whether a call is overturned. So this section is about to test whether the variables are independent of each other or dependent of each other. Your null hypothesis should be the variables are independent, and your alternative should be the variables are dependent. So let's see which one was selected here. You see here, gender of the tennis is independent of whether a call is overturned, and you're going to notice that H1 means dependent or is not independent of whether a call is overturned. Now, how do you find the test statistic using StatCrunch? Watch me carefully. Open in StatCrunch. Go to Stat, Tables, Contingency Table with Summary. Select the columns that have the data, which successful challenge, and press down the control key. And now for the rows, select, just the heading of the rows, which is men, women. It didn't have a title, so I'm going to select this one right here and hit compute. And look, this is the test statistic. So the test statistic is 44, and look at the p-value is very small, so you reject the null hypothesis. And when you reject the null hypothesis, you support the claim that the variables are dependent of each other. This is how you do it using StatCrunch. I'm going to show you how to do this using the calculator. Okay, using the calculator, how would you key in this table into the calculator? Watch. You go to second and matrix. You go to edit. This is a 2 by 2 matrix. You just count the data. There are data in 2 rows and 2 columns. So you just press enter, select a 2, and put another 2 here, and enter your data. So I got 408. Enter. What was the other number? 610. Enter. 352. Enter. And what's the last one? 952. Actually, this is a chi-square test. It needs the observed and expected value, but it's enough to put the observed values. The calculator can figure out the expected values here. And then you go to stat, tests. It's a chi-square test, not chi-square goodness of fit. That's 12.1. That's chi-square test. You see, observed and the calculator is going to put the expected value in B for you guys, and hit calculate. And look, we got the same thing as StatCrunch. And look at the p-value. It says 2.6 e minus 11. E minus 11 means you move the decimal point 11 digits to the left, so it is 0. Okay, and the p-value is small. Now, if you want to see the expected values, let me show you the expected value. Press second and matrix. Press B. Scroll down to B, press enter, and look, these are the expected values. For 408, the expected value is 333. For 352, the expected value is 426, and so on and so forth. All right, this is another one from section 12.2. In soccer, serious fouls result in penalty kick with one kicker and one defending goalkeeper. The accompanying table summarizes results from 300 kicks during games among top 10 teams. In a table, jump direction indicates which way the goalkeeper jump, where the kick direction is from the perspective of the goalkeeper. Use a 5% level to test the claim that the direction of the kick is independent of the direction of the goalkeeper jump. So your null hypothesis will be the direction of the kick is independent of the direction of the goalkeeper, and your alternative will be the direction of the kick is dependent of the direction of the goalkeeper. Do the results support the theory that because the kicks are so fast, goalkeepers have no time to react, so the direction of their jumps are independent of the directions of the kick? All right. So this is the null and the alternative. Jump direction is dependent of kick. Jump direction is dependent of kick. And I'm going to show you how to find the test statistic. I'm going to use StatCrunch. Open in StatCrunch. You go to Stat, Tables, Contingency with Summary. We're going to press and hold down the Control key to get them. And then the row label will be this thing right here. Hit Compute. And look, guys, you get the p-value and you get the test statistic, which is 6.4142, and look at the p-value, it's big, so you fail to reject the null hypothesis. Look, fail to reject the null hypothesis, but p-value is more than alpha. There is not enough evidence to warrant rejection, since he says test the claim that the jump direction is independent of kick direction. That means the claim in HO. And since we fail to reject HO, we say we don't have enough evidence to reject the claim. You can see that right there. And yes, the results support the theory that because the kicks are so fast, goalkeepers have no time to react to it. That's indeed true. Okay, now we're going back to chapter 11. An insurance company collects data on seat belt use among drivers in a country. Of 1,900 drivers 30 to 39 years old, 22% said that they buckle up, whereas 485 of 1,800 drivers 55 to 64 said that they buckle up. At 1% significance level, do the data suggest that there is a difference in seat belt use between drivers 30 to 39 and 55 to 64? So we want to test that P1 is not equal to P2. This is a two proportion Z test, guys. So I'm just going to take you back to the calculator and show you how to do that on the calculator. So we'll just go there. You go to Stat, Tests, 2 prop Z test, enter. Okay, X1. X1, how many successes? He says of 1,900 drivers, 22% buckle up. He didn't give me the number, but look what you can do, guys. You can take 0.22 and multiply by 1,900, and then you can find X1. And that's 1,900. For the second group, age 55 to 64, he says 485 of 1,800. So he gives me X, 485. And of what? I forgot. 485 of 1,800. we need to check that P1 is not equal to P2. And here you go. Z is negative 3.49, 3.5. And look at the p-value. It's very small, guys. E minus 4. So E minus 4 means do move the decimal point 4 digits to the left. So it would be 0.000467, which is less than alpha. That's all matters here. To 3 decimal places will be 0.01. So there is enough evidence to reject the null hypothesis, and there is enough evidence to support the claim when you reject the null hypothesis because the claim is in H1. Okay. Now we're back to 12.2. The contingency table shown to the right gives a cross-classification of random sample of value for two variables, x and y. Find the expected frequencies. Determine the value of the test statistic. Decide at the 5% level whether the data provides sufficient evidence to conclude that the two variables are associated. Associated means related. So your null hypothesis, guys, will be the variables are not associated, they are independent, and the alternative will be they are associated. And let me show you how to find the expected values and the test statistic. I'm going to use the calculator this time. It's faster and easier. So we're going to go to second and matrix. And we're going to go to edit. We're going to do 2 by 2 because this is a 2 by 2 and enter the observed values 40, 30, 20, 50. Okay, now guys, we're just gonna quit and go to stat, tests, chi-square test. The calculator is gonna put the expected value in B, and that's what he's asking for. And not only that, it's gonna give us the test statistic. Test statistic is 11.67, and look at the p-value, it's very small, it's 0.0006. So that's the test statistic. And the p-value is less than alpha, we reject the null hypothesis. And we conclude that there is enough evidence to support the claim that the variables are associated. Now let me show you the expected values on the calculator. That's what he wanted. You just press second and matrix, and you just scroll down to B, guys, which is 2 by 2. Press enter twice, and these are 30, 40, 30, 40. And look, 30, 40, 30, 40. Which one is not true here? Well, you can see the last one is not true because a type 1 error is making the mistake of rejecting the null hypothesis when it is true, and it says when it is false. So that's a wrong statement. Determine whether the samples are independent or dependent. A data set includes the morning and evening temperature for the last 80 days. It is the same day in the morning and in the afternoon. Same day, morning, afternoon, that means the samples are dependent. Okay, we are trying to pair them. On Monday morning, Monday afternoon. So it's the same Monday, before and after. Next question. Listed in the data table amounts of strontium 90 and a simple random sample of baby teeth obtained from residents in two cities. Assume that the two samples are independent. That means this is two sample t-test once he says the samples are independent. Selected from normally distributed population. Do not assume population standard deviation are equal. That means pooled is no. When he says do not assume population standard deviations are equal, then pooled is no. Use a 10% significance level to test the claim that the mean amount of strontium 90 from city 1 is greater than that of city 2. So need a greater than. It's right here, guys. This one. Always equal sign in the null and greater sign. So it's a two sample t-test. Let's see here what we have. Oh, okay, I'm going to do it in StatCrunch here. So open in StatCrunch. Go to stat, t-stat, and the calculator will be two sample t-tests, but you have to put the data in L1 and L2. Two sample with data this time. I don't have a summary. City 1, City 2. Okay, you only select the pool when he says population variances are equal or population standard deviation. Since he says assume they're not equal, so it's off. Leave it like that. And we want to test that mu1 is bigger than mu2, so you choose the greater sign. Compute. So test statistic is 1.458347 and p-value is 0.082. And we're testing against what alpha? 10%, so that's less. 0.08 is less than 10%, so you reject the null hypothesis and you say there is enough evidence to support the claim that mu1 is greater than mu2. If you want to use the calculator here, guys, this is what you have to do. You have to go to stat, enter. You put the cT1 in L1, cT2 in L2, and then you go to stat, tests, 2-sample t-test. You select data, L1, L2, leave the frequency as 1, 1, choose mu1 greater than mu2, and then pooled is no by default here because it says assume population standard deviation are not equal, and then hit calculate, you will get the same results. I'm not going to hit calculate here because I don't have the actual L1 and L2, I just different L1 and L2 here. And one more question. Same question here. Listed below are the time interval between eruptions of a geyser. Assume that the recent times are within the past few years. The past times are from around 20 years ago. And that the two samples are independent. Independent means two-sample t-test, selected from normally distributed population. Don't assume that the population's standard deviation are equal. That means pooled is no if you use your calculator. Does it appear that the mean time interval has changed? Has changed, guys. It's not positive, it's not negative, not increase, not decrease. So you do different from. That's what has changed mean. So we need to test that mu1 equals mu2 and mu1 not equal to mu2. You just go here, open in StatCrunch. You go to data, stat, tstat, 2-sample, with data, column 1. Don't worry about where, you don't touch that one. Past, and not equal is good here, that's what I want, and compute. Tested statistic is negative 2.03, and look at the p-value, 0.05. What alpha is he giving me in the problem? Oh, 0.05, 10%. This is less than 10%. That means you reject the null hypothesis. But then he asks you to do it at 0.01. That's bigger than 0.01. You fail to reject the null hypothesis. So at 10%, you reject the null hypothesis and conclude that the mean time have changed. But at 1%, guys, you fail to reject the null hypothesis and conclude that there is not sufficient evidence to support the claim. All right. One more thing in StatCrunch that you notice here that you haven't used. Z-stat. We only use Z-stat if it gives us the population standard deviation in the problem. Otherwise, it is a T-stat. That concludes the review.